Well, good morning, folks. I think we'll go ahead and get started. I hope everybody's having a good morning so far. Let's go ahead and open up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, thank you very much for the chance to be working with each of the students in this course. I pray that the material that we cover will be clear, educational, and hopefully enjoyable as they get a chance to prepare for their careers as being engineers. Pray that you would help them in their spiritual formation, Lord, that all of the times, the courses, the encounters that they've had with Scripture, getting familiar with the content, and also how we do theological assessment, drawing out concepts, and then being able to apply that to other places in our lives, that you would help them in all that, and that you would help them to store these things, these memories, these experiences in their heart and be able to use them in their time of need in the future. Also pray that you would give them interesting and creative ways for faith integration. In Jesus' name we pray. Amen. Okay, well, we're going to continue to our journey in the whole system engineering life cycle. And so this is going to be the first lecture that we're going to be talking about in this post-production and environment. And so I'll go through a handful of charts that will give us a sense of what it's like in that kind of a mode, and I'll also introduce a few other things. I'll go back to the James Webb Space Telescope as an example, just to be thinking a little bit more about that in production, as well as I'm thinking about Tesla and how they actually do their production. And so those will be a little bit of an aside on a few topics that I'll make sure that we cover. Then I'm going to transition over to our internal block diagrams, and I'll be providing a little bit more context and showing some examples in Cameo Systems Modeler as well as visual paradigms, and also refer to our practical guide to SysML. And so those will be the things that we'll have. So we're talking about production, and so this is a system engineering course, and so we're thinking about how a system engineer actually engages in that process. And so this is where we think, well, where and how does a systems engineer participate in the factory operations and production? The objectives of the production phase are to produce sets of identical hardware and software components. And so that's not going to be the case for James Webb Space Telescope, but if they wanted to, they could build a print. But I'm thinking of Tesla as an automotive manufacturer might be a good example to think of that production line. So they're exact copies. You assemble components into systems that meet specification and distribute products, systems, produce systems to customers. So an analogy with something like Tesla would actually be quite applicable for that. They literally do deliver it to your doorstep if that's what you would like. So essential requirements are those that the produced system performs as required. So it has to meet the requirements. You want it to be as affordable as possible and functions reliably and safely as long as it is required. So satellite, a typical number is they designed for a 10-year lifespan. I don't know what the exact number is for automobiles, but I think that would be a realistic idea if you didn't have something for a basis to start out with. So essential requirements are that I mentioned this, that they're produced as that it performs as required. And so now we're getting into this transition from development to production. So it's not on building things, it's producing identical copies. And you have to be thinking about the operation of production and also having a production knowledge base. NASA has something called the technology readiness levels, TRL levels. They also have something called manufacturing readiness levels, MRLs. And so this is where we're getting into this sense here. I know one of you is looking at a nuclear power plant and the whole Department of Energy. The way one of the things that they do is they manage the nuclear weapons that we have for protecting our country, and so they have the design agencies and then they have the production agencies. And so there's a little bit of a distinction. And so we're getting a chance to see some of that being laid out here. So now we're going from the integration and evaluation. So this is, we have a design, we have to integrate it, evaluate it, test it, and then we move into the production systems. We qualified our first article, things look fine. We have the specifications that they're supposed to meet. Now we get into this different type of production and deployment. And so tooling and test equipment, trying to streamline and make the production line as efficient as possible. Um, I think I've mentioned every once in a while about microelectronics, that when you develop a chip line that is, say something like Intel does or whatever, and they've gotten these things so small, and the actual cost to set up a production line for microelectronics can actually cost billions of dollars. So literally, they get it set up and they run it 24/7 for years. And so what it does, it gets the unit cost down to an affordable range, but there's a lot of things that are done when that production line is set up. And I'll show you an image of a Tesla production line. You'll get a chance to see how it's been very much optimized. And so that's what we're going to be talking about here. And then in the next chapter, we'll be talking about operations and support. And I'll reflect back on how that works for the James Webb Space Telescope to continue along that theme that I've been going the whole process through our course. So here we see the production phase overlap with adjacent phases. And so we have the integration and evaluation phase that came before. And once you completely qualified that first article, then you get into this production. So you're trying to get into having all of the things in place that you need to do production, gradually go from low rate production to full rate production. And then you're deploying those things. And so for a satellite example, I'll just use GPS as an example. To get the whole constellation and get the whole benefit of GPS, you need at least 24 satellites in orbit. And so it gives you an example of a space system doing that. So for engineering for production, concurrent engineering is something that needs to take place. And so now you're doing your engineering for your production. And so that's a different thing that you're having to deal with. And so in this area, it is a process of introducing production considerations during development. And so the production actually leans back into the development to see, well, how did they do this first article? Are there things that we can take in terms of lessons learned? And then production specialists and other specialty engineers are key members of the design team, and they're taking notes and to see how they're going to go into this production rather than design. Therefore, system engineers must facilitate communications among these team members. And so that's another key feature of what system engineers do. The decision to begin new system development must be demonstrate its need, technical feasibility, and affordability. So these are all things that not only you're looking for production, but you're also looking at what are you going to do the next time around when you're going to be doing something. So you're going to have like a block build that's even better. So James Webb Space Telescope is supposed to perform even better than Hubble. That would give you an idea of that. So you're trying to deal with the production risks. And so these are influenced by the nature and maturity of the associated manufacturing methods. And so if you have a well-known company, they've actually have built a variety of things. And so they're continuing to try to minimize those risks. And they are heavily weighted in trade-off analyses of system alternatives. Successful production requires that the new production process and materials they have to be validated before acceptance. Component interfaces are compatible with manufacturing processes, and factory test equipment is validated and ready. So these are all things that happen before you're going to get into this high rate production. So the latter is typically demonstrated by producing prototypes that have demonstrated product performance. So you go from low rate to high rate production. So there is concurrent engineering throughout the development cycle, and there's a lot of different things that are involved in that process. You can have these are going to be referring back to needs analysis, concept exploration, concept definition, advanced development, engineering design, integration evaluation. And so ultimately, if you're going into production, you're going to have these production experts are going to have some level of involvement through those areas in which the system engineering view of your design has been validated. Unexpected incompatibilities at component interfaces have features that have to be looked at. They are often the first discovered during the integration of prototype components. Thus, production folks have to be mindful of that. Corrections of incompatibilities may themselves produce new areas of incompatibilities. So that's one of the reasons why the production team needs to be involved early on. System engineers must be knowledgeable of factory production and test acceptance processes, because ultimately they're gearing things for that direction. And so direction and control of production differs from system development in that there's different tools. Now you're trying to minimize the individuals that are used. You have different skill sets. You have more technicians rather than engineers. The experience base and skills will be of a different sort, and a different team of specialists will be primary for those areas. Production risks are frequently not revealed until production prototypes are fabricated and tested. Remedial action is likely to cause expensive delays. Therefore, system engineering expertise is crucial for resolution when you get in that environment. Okay, this is my first aside. This was another graphic. It's actually a mission system architecture diagram for the James Webb Space Telescope. Some of this I've already talked about, but it kind of gives you in a nutshell what is going on for the James Webb Space Telescope, how it goes into operation. And let's say that you wanted to build another one, and so you're going to populate it at another point where you can get, increasing your image production by orders of magnitude if you have more of them launched. And so this would be the things that you would have to be thinking about, that you're starting out with building your system. Here, you have a complicated way of how you deploy it to where it's going to be operational. All that needs to be figured out. There's a lot of different links that you communicate it when it's on the launch pad, when it's in transition, going to its final orbit, while it's being deployed, early checkout in its deployed state, and then finally goes to full operation where it is right now, and hopefully it's going to last for a long time. So this isn't so much focused on production and in terms of an assembly line, but I wanted to just have you think about this. If I was to pretend this was the GPS satellite, you could see that it's not only that you drive this up to somebody's doorstep like a Tesla automobile, you actually have to put it into a very difficult orbit. And so that is part of what would have to be done in that kind of a situation. So we talked a little bit about it, but let's have a few more thoughts on this transition from development to production. So stresses on the transition from development to production results from insufficient funding. And so you want to have that overlap in the beginning because it's going to pay you back in the end. Maybe there's little or no reserve for unexpected problems. There's always some problems that you're going to have to deal with. There could be too little testing of production prototypes, and schedule held firm even though problems exist. And so if the overall managers are saying we have to meet schedule because there's some funded milestones that are related to those, there could be unfortunate stress that's trying to have them do that, and then they're not fully fleshing out what's going to be issues further on in production. Transition to production is the most critical period for continuity of operations. You get some of this change of personnel, and so that can be something that could cause some issues. And so that is something where one of the roles of a system engineer can be one of those folks that help to maintain that continuity. So transition to production is critical in the configuration management process. You have to maintain positive control of your design. Documentation cannot lag behind the change process. They need to know exactly what they're building to, not a 1 or 2 cycles before. And so that would be an example of something that needs to be captured. There's still transition in management and participants. And so there could be folks that are design managers and then there's production managers. And so you want to make sure that there's incentives to make sure that that transition goes smoothly. And there can be various problems in transition. It can be technology related, making sure that you have the right specializations that are still those folks are available. There could be competition with other programs, and so you have a subject matter expert that everybody wants in the company. And so those are things that you have to be thinking about. You have to be dealing with product preparation and product configuration management. So here is an image that I found. It's a little bit dated. I think it may be on the order of 5 to 10 years old. But if you were to look down this assembly line for Tesla automobiles, one of the things you'll notice is there are no humans in the loop. So it's all automated. And guess what? It can take a while to get a production line to operate like this. I'm not showing a production line for chip manufacturing, but it's the same type of an idea. Robots are really good in that they repeat the same operation exactly again and again and again. And so the tolerances can really be brought down to a very precise level. And so there, if you're going to have an assembly line like this, it means that you're going to have to be investing a lot in the automation. And so those are the different kind of skills that you would need. This is different than what you're doing in terms of you're starting out with developing a new model and you're trying to do all those trade-offs, things that we've talked about already. But ultimately, this was a vision for Tesla that they wanted to go into this kind of a production environment. So that just gives you an idea. So in terms of production operation, maybe that image will help you as we go through these next handful of charts. Planning, designing, implementation, and operation of your production systems are tasks of comparable complexity developing the system itself. So just because you have a great design doesn't mean that is manufacturable. And I've heard some different labs that what they did is they're really good at doing prototypes, but then they got asked to create more than one, and they didn't have the kind of skill to do this production, to build to print. This is where we're at when we're in this production operations. And so architecting has a different kind of a focus here. And so architecting of the production system requires acquisition of extensive tools and equipment, coordination with component manufacturers. You have to make sure that all of the components are available so you're not going to be delayed. Coordination, like I said, organization of tight configuration management, establishing an effective information system with every organization that is affected, training. You have to be able to accommodate both for low and high rate productions. And so in the very beginning, this would be a low rate production where things were going slow. And then they can go to a point that where they could be producing a fully manufactured car, say in 8 hours. And then you want to be able to promote flexibility to accommodate future product changes. All of that has to be thought through. So there can be specialized components, which often represent different product lines and pose special problems. So maybe for Tesla, this would be the overall integration of components to the main car frame, but there could be some other component lines that would be focusing on making the batteries. They make the batteries themselves. And so that would be a sub-assembly line that would have to be organized before you get there. Computer-controlled manufacturing methods greatly increase speed, precision, and versatility of factory operations. And some of you may end up getting interested in industrial engineering, and that would be one of the key things that they would be thinking about of doing computer control in a factory operation environment. So here is just a diagram that gives you an idea of what's going on in a production environment. And so you have to have all of the suppliers getting all the information that you need to maintain this this operational production line always operating, and say it's operating 24/7. And so you need all of the subcomponents that are constantly being passed in engineering, and it's more focused on production engineering, are making sure that everything is fine, that they're doing quality control to make sure that everything is operating fine with the production line. And finally, you have the finished products that then go to consumers, and that would be how that starts to flow. There's also a knowledge base that is focused on production. So system engineers must acquire a basic knowledge concerning production processes to be able to be capable of guiding the engineering of a new system. So they must focus on all of these things, advanced technology, new production processes, for the risk areas as they may be affected by production. So it may be a great technology, but if you haven't got the recipe really figured out quite precisely for production, that's going to be a problem. So the system engineer's component knowledge base is going to be in a variety of areas: electronic components, electro-optical components, electromechanical components. So all kinds of different components, mechanical components, thermomechanical components, software components that are all going to be put into this production environment, that you need to make sure that these continue to be operating and being available as needed. And plus there's production processes, and so you want to be constantly doing this monitoring, observing the production operation, production organization, and the production standards. All of those things are things that come into play that a system engineer is going to be focusing on. Okay, we did a quick tour of thinking about what a system engineer does in the factory. We talked about the transition from engineering as it gets into production. We talked about the transition from development to production, gave some perspective on production operations, and finally, what is important in production is you need to have a production knowledge base be part of what's going on, and a system engineer is going to be key in ensuring that that takes place. So let me just get a quick round the room. Did you guys follow that? You can just do a thumbs up if you like, just to let me know that you guys are tracking with what we've got here. Okay, good. So I'm going to transition out of going through some PowerPoint now. And let me just spend a few minutes to go over the practical guide to SysML. And so this is another resource. I hope that you're taking advantage of it as you're doing your project development. And in chapter 7, they deal with how you do modeling with blocks. And so the way that they decided to develop this chapter is not only dealing with blocks, but also internal block diagrams. And so that's the reason why I'm reflecting back on this chapter, and you'll quickly see what I mean by this. And so I'm not going to read this, but you can see that one of the things that they have is a surveillance system, and so Freudenthal talks about that in his textbook here a lot. And then we can see various ways that we can see an internal block diagram being part of this. And so this would be for the camera. So here we can see all of these different elements that are a part of the camera, but now we're going to be focusing on it from a different point of view. And so this is looking at how the light goes. So you're thinking about the optics, how you're going to be mounting it, and how things flow. And so there's a linear flow from left to right. You have a polarizer. So this is one of the things, just maybe you're familiar with polarized lenses for sunglasses. You can be using this for a all-weather day and night camera that would be part of a surveillance system. So that just give you the first internal block diagram that they referred to as they develop things here. You also get a chance to see different ways that they're using the internal block diagram. We've talked about this a little bit. So I'm just paging down here. So you can see here, this is now the mounting assembly. And this is just trying to show the aggregation of things that are actually part of that mounting assembly. So that is still within spec that you could be using the internal block diagram to do that. Here, this is talking about the connections for the camera. So you go between the protective housing to the mount, the camera module and the electronic assembly. And here we're not showing the ports. We're not showing directionality. That's something else that we could do. And so this could be an example, maybe a higher level IBD that you have here. We see some other examples of encapsulation. And so you can have within one part of this camera, the mounted assembly, you can be talking about the gimbals. And so here we have the azimuth. And so that can be something that you can be starting to highlight. This is some more details of showing the nested connectors of an internal block diagram. As you can see, a part within the mounting assembly is actually going to a part in another part of the camera. And we see that a couple times. That's perfectly fine within the specification. We're still not showing ports. We're not showing directionality for the purposes of that internal block diagram that is adequate for what is trying to be addressed. And so those are just a couple of things that I wanted to be pointing out. Let me now just click over to, first of all, visual paradigms. So I showed you several examples on Tuesday, and so this is now just repeating that. And so over on the right for some of these diagrams, what I did is I put in the block that this is related to. And so we can see now these are directional ports. So just to give you an idea. So you can either have an input, an output, or in-out. And so this is set up as an out, so the arrow goes to the right. So the flow is from left to right. If I was to make it in and out, it's going to have arrows going in both directions. So that's something that you could add to a module. Just click on a port, and you can either do a bidirectional. So there's a couple different choices that you can be having here. So maybe just start with just having a port, or you could start to augment that by giving it some directionality. So here is one that I showed also. This was now just showing for the power subsystem, and this actually, all of these ports are bidirectional. So if I just click on the specification here, it says in and in out rather than in or out. So those are things that we're seeing there. And all of these flow ports are shown here. We have a couple standard ports, and so these are things that are laid out like that. So And so these are a couple of different things that you can have. You can have a flow port, a full port, or a proxy port. All of those things are within the possibilities of what you could be generating for a internal block diagram. And then there was one other one I'll show you. This is for a sensor, and I showed just, for illustration purposes, some of the blocks that are related to this. And there's a couple other things that are here that aren't necessary, but these are just showing you a couple other okay. So these are attributes. And so this is for the payload. And so here we have the sensor availability, and this was threw in something else for NASA standards. That would be something that I could be including if I wanted to, but this is the guts here of showing the sensor payload. And so here I have just some general ports here to start out with. Then I have a directional flow port here. So here, this is for the EOIR sensor. And so we have flow ports here, FPA here. So that's a flow port. So a variety of flow ports. We have standard points, the sensor command in, sensor telemetry out, and sensor in. So that's there. Just I'll move them a little bit so you can see what I'm referring to. And these are some nameless ports that I have that are also part of that. Okay, so what I would like to do in a few minutes is have you tell me a little bit more about what you're doing with your project, and maybe have a little bit of a dialogue. And I've enabled sharing that you can share your screen if you would like. And so in Freudenthal, I showed you this, where here we can have different elements within this this block. And so in there, here I can see an internal block is connecting to the another block. So that would be something that's within the possibility of what you could do. Here is something that gets a little bit more complicated. Unfortunately, this is something that visual paradigms, I have not found a way to be doing this, where it actually shows it right on the edge of the diagram. And so to just keep you in reference, this is part of what you can be doing with the spec. This is showing ports, and it's, instead of showing the arrow in the port, it's actually showing it on the going between elements. And so this is for navigation and control. That's what this subsystem is. This is for propulsion, and this is for a satellite. And so we can have the command and telemetry goes into the propulsion software. You have a propellant tank. And so this is what a lot of satellites do, is they have tanks full of gas. And what it can do, so say if it wants to do what's called a delta V to do some station keeping or redo its orientation, this is where it's starting to take some of that gas through a propellant line, and then it's going to put it into a thruster, and that thruster is going to have a nozzle. And so this is how you could start to have a certain amount of delta V that you could be applying to correct the position of that satellite. Here is a power subsystem. And so if I was to go back and forth between this and what I was showing for the one that I did in visual paradigms, we can see that they have solar panels. They're showing that. They have the battery here. They have the power management. And so you could just go back and think between these two. And so this can be the kind of thing like, well, are these equivalent or did I miss something? And so thus you can be using your model as a way of trying to refine your design. And so if I was to switch back and forth between these, I could start to make some observations about that. Here we have a communication. And so here we have the diplexer. I was showing you that in the one that I had for communication. Didn't actually call out a diplexer, but the diplexer would be in this antenna module. Here they explicitly talk about that. So you have the receiver and the transmitter actually go to the diplexer and then head out to the antenna. And so this is that's one of the things here. And so they actually have two antennas, a low rate antenna, so it would be a smaller aperture, a large high rate antenna that would be able to have a lot higher data rate. And so those just gives you a couple ideas of what you could do and going in details in an internal block diagram. So some of these diagrams can get quite complicated. I'm not going to talk about this one, but just to show you this briefly. And so this was now kind of giving us a mission context. And so now we're showing more details inside this to get more specific about what it is that we're talking about for a mission. And then just very quickly, these last two are extremely complicated, relatively speaking. And so you can see that there can be a tremendous amount of details that you could be trying to do in an internal block diagram, maybe so much so that you would want to break it up into multiple diagrams. And so this is looking for a spacecraft subsystem, and you have all these different things that are connecting to it and going in and out of that subsystem. And so that one's complicated, and this one's even goes into more detail than that. And so that just gives you an idea of how that might work. Okay, well, let me go back to you all. Let me just do a quick round the room. Are you following what I shared in terms of internal block diagrams from that discussion? Okay, good. Other folks? All right, well, let me stop sharing my screen for now and see if anybody would like to if you would like to share what you have in visual paradigms, feel free, or if you at least would like to talk about what do you think you would like to utilize, what would you like to develop in more detail with your internal block diagram.
Yeah, I mean, I can go.
Okay.
Share my screen. I haven't really connected anything, but I wanted to. Well, can you see it?
Yeah, I can see it.
Okay, cool. I just wanted to do like the avionic system, for the missile,
Mm-hmm.
and so I pretty much have, I think, like what I wanted. It like I just want to show the connections and kind of what could happen
Yeah.
when I try and make like the port here. It gets rid of this name. Do you know why? Like it just.
Okay. Try and delete that port.
Uh-huh.
Okay, now go to the ADCS controller
Uh-huh.
and now go to that little thing that comes up in the corner,
Yeah.
create the port there. Now it's associated with that module.
How come it like keeps renaming it to like block 8 or whatever? Because before I had like this name.
Okay, yeah, this is another thing that's important for everyone to see. When I look at what you have here,
Mhm.
an internal block diagram is supposed to be focusing on one block.
Yeah.
What you have for each of these modules are referring to a different block.
Wait, what?
You see that that one's for guidance. You go to the one to the left, it's internal navigation.
Yeah.
And the one next to that, it's global navigation satellite system. Each one of those are different blocks.
Yeah.
And so you want everything in general, what you want for a internal block diagram is you want it to be related to a block, and then you're going to be spelling out the details of that block.
Okay. Okay, I see.
So otherwise you're going to run into a lot of these problems like what you're having here.
Mhm.
Um, why don't you let me drive for a minute and I'll come back to you and show you what I mean, okay?
Okay.
Okay, so back to visual paradigms. And so let me do a diagram. Let me do a new IBT. Okay, so if you guys haven't done this already, this is where I'd recommend you go ahead and do this real time with me. So I like to just name it because visual paradigm doesn't automatically put it in. And so let me think of something I haven't done yet. So I'm naming it. So this is what I'm trying to explore the details and what it'll do. Okay, now when I create like so now I want to have everything here focused on a control subsystem. So if I wanted to create a new part property, okay, so this is an example when you get an error message. So it didn't do something quite right. So let me delete this one. If this doesn't work, I may have to restart my visual paradigms. I'm not quite sure. There it is. This is what I was. So you want it to be related to a block. So I was talking about control. So maybe I'll make it attitude control subsystem. And so this is the first step that you want to do. And so now it's related to a block. So I'm going to rename this one. Let's see. I'm not sure why it didn't change. Okay. So now I'm trying to do things related to an attitude control subsystem. So if I'm going to be adding a new part, so now what would be some things that I'm going to be focusing on? So I'm going to make them all. related to that attitude control subsystem. Give me a second. I'm trying to. Yeah, so all of these they're related to communication. And then I've put in a name to them. So these are all part of this communication. So this is going to be the association. So you can see how I have all this over here. So maybe I'll call this a gyro. That would be part of the um on this. And I have like a computer. So those would be some examples of what you would want. So let me stop sharing my screen and turn it back over to you, Nathaniel, if you want to give that a go. You may want to make sure you hit save, but then you can create a new internal block diagram. And we can maybe just put one or two modules in there and see if that helps you.
Okay, I'm sharing it right now. Okay, so new block diagram. That's fine.
Yeah.
Change it. And so you said go like more specific, right? So
Now this is where you're trying to go that next level of detail. So you need to you want to relate it to a block you've already created. Okay, now you got that. Okay.
mhm. So then I make a part.
Yeah. And it's going to give you that. Now you want to relate it to something.
Okay. And
You
so I
could go ahead and relate it to that same thing, or whatever it is that you're doing. You want everything related to that same block or sub block.
so something like that, and then I
Yeah.
change this.
Yeah.
Okay.
That's what I'd recommend that you do. And now it shouldn't change the name. So if you were to add a port to it, you could try just
So that's fine.
yeah, move it around, make sure it's connected.
Yep.
Okay, good. Yeah, so that's another way you can add a port to that. And that's a bidirectional port. You could actually change it, right click it if you open the specification if that's not what you want. But you don't have to do that, but that just gives you an idea.
Okay. So if I want to show like what's in the CPU, then do I actually have a block for the CPU, or just that's the name of the diagram? Like, would the folder be the CPU, and then everything's in it?
There's a lot in the SysML specification. And so um, so technically you don't have to have everything that would be associated with the missile CPU on this diagram. It will allow you to do that. But so why don't we just go back for a second and say, what is it that you were trying to explore in the next level of detail? You were saying about the missile guidance, I think you were saying.
Yeah. Yeah. I just wanted to kind of show like the
But then what you want to have is you want to make sure that you have a block named missile guidance. And if you don't, then you would want to go to a block definition diagram and make sure that you have that block that you then want to explore.
Okay. Yeah.
And if there's, things that you've related to that block, so for example, the guidance, it has a missile CPU that is an element that's related to that. I think that would be something that you could do. And I think that would be okay with the specification.
Okay. So like, is this bus too high of a level or is this fine?
When you, I don't know how all of these blocks are related to one another in a block definition diagram. So
Mhm.
I don't have enough information with what you've listed here to give any more information to why you might be getting an error that you got.
Mhm. That, I mean, that's all right. It's just like, should I focus more on like one thing?
Yeah, I'd start focusing on one thing for now. Okay.
Okay. Yep. Got it. Thank you.
Thank you, Nathaniel. Anyone else want to get a chance to share what they have, or we can have a dialogue about your project?
I haven't really started like the diagram, but I was wondering if you think I could do it for like the engine block.
Yeah, sure. That would be fine. So, with an electric vehicle, you think there's the battery, there's power conditioner, maybe. It needs to go to an electric engine, then go into your transaxle, to your wheels, however many elements that you want to spell out, that would be fine.
Okay, so it's more like how it connects to other blocks as opposed to just inside that one block, like how the engine itself works.
Well, then, so if you're thinking of what, you're gonna have to tell me what you mean by the engine block for your car. I wasn't referring to the right things if I was just thinking it. So the engine block, you have the components of a motor. So it needs to, so the DC or an AC motor, what are the components that are in that motor? And so those are some things that you would have to be fleshing out in your diagram. I don't know if I can come up with those things off the top of my head, so I won't try and do that. Can you think of two or three elements that would be in the electronic motor?
Not in the like, or wait, for the electric battery or for like the actual, like the gasoline engine. And
I'm not, so you tell me what you want to do in your project. So if it's a hybrid, then your engine you can have a gas engine and an electric engine. And so all of that's going to be part of the engine. And so you need to be figuring how that would be. So maybe if you were considering that, you'd have the gas engine and the gas engine subsystem and the electric engine subsystem. And then maybe you would go to some more details below that.
okay, but that could all be on one block diagram.
Internal block diagram, yes.
Okay.
So your block would be engine, and then you're going to expand that engine to be thinking about these individual components within that engine.
Okay.
Anyone else wants to share? Kyle, you want to give us an update on what you're envisioning that you're going to do for yours?
Really, I'm just still trying to figure out what exactly I'm gonna need to do as far as like different parts of the thing.
Okay, would you have visual paradigms open?
No,
Yeah, you should have it open because this is where we're trying to do hands-on, giving you a chance to see how to do this. And anyway, that's what I would recommend.
okay, I can find it.
Well, I'll go to Jonathan. Jonathan, you want to share what you have?
Yeah, I haven't done too much on the diagram itself yet, but I was thinking of doing it on the reactor block I had.
Okay. Hmm. Well, how about this? We can spend a little bit more time going over this. We have one more diagram that we're going to be covering, a parametric diagram. And so we'll be starting to talk about that. And we'll have a couple of weeks that we can do some review. And if anyone wants to add to, modify, or just share what you have on some of these diagrams, we can go ahead and spend some more time next Thursday on and the later weeks after that talking about that. Okay. So so maybe just start out with something simple. And I'll just share my screen just for another minute or two, and then we'll finish up for the day. So you can see how all of these are related to communication subsystem. They're all, this is, and when I create a block, I'm sorry, when I create a new property, okay, this is a separate issue. I don't want to get into what's causing this. It's where I've actually put this folder, this diagram. And so that's a separate issue. But if I was to go to this new one that I created, so this is the attitude control system. So I can easily connect these to other blocks, other properties, I should say. I'll just create a port. So I want to connect this to another port. No, it's not. Okay, so that's how you can go about connecting one to another. I wanted to make this a different type of port. Yeah, I think I selected the wrong kind of port here. I just created a let me okay, let me add the attitude control subsystem just to give me some sense of what I've got here. So this is the block I was trying to find. So if I was to, let me make sure I did this right. So if I was to, maybe this. Does this change? Okay, yeah, good. All right, so this is the block that I was starting to modify with some of these things here. So this is showing that this is a standard port. And so that would be one of the kind of ports that I could create. If I wanted to create a So I wanted to create a new flow port. That's what I was trying to create here. So you can have these different kinds of ports. And so depending on what you're trying to do, and right now this is a bidirectional flow. I could change it to an input port. Could change it to an output port. Or I could change it to a bidirectional port. All those are possibilities. Okay. So why don't I leave this that you guys are working on your internal block diagram. I was trying to give you some ideas of things that you might want to do. I showed you both in Visual Paradigms as well as Cameo Systems Modeler. And so this maybe just gives you an idea of how that looks. So Abby's asking, how did I add this block to this? And so what I did is I went to the block diagram that had that, and I just did a copy within Visual Paradigm Modeler. And then I went to the internal block diagram, and then I just did a paste view. And that's what I did. Okay. Any other comments or questions folks have? All right, well, God bless you guys. I'll look forward to seeing you next Tuesday. Hopefully, once we get past some of the mechanics, we're going to want to then start to try and draw this all together. What have we started to figure out for our projects as a result of doing all this modeling? Okay. All right, well, I'll stop sharing my screen, and I hope everybody has a good rest of your day. Take care now. God bless.
Professor.
Thank
Thanks.
you.